PKC on indistinguishability, obfuscation, and zero knowledge. Before we start, I have an announcement. Someone lost their Apple stylus. If you can come get it if you know who has it, whose it is. All right, so the first talk will be on non-interactive publicly verifiable delegation of committed programs, paper 161, by Riti Gosal, Amit Sahai, and Brent Waters. And Riti will be giving the talk.
Hello. Yeah. Yeah. Hi, everybody. So I'm Riddhi Ghoshal, and I'm going to present my joint work with Amit Sahai and Brent Waters on non-interactive, publicly verifiable delegation of committed programs. Let's start with the problem setup. So we are working in a setting where, let's say we have Alice, who is a trusted program author who has written some program P. And Alice wants users over the internet and around the world to be able to compute things using this program P. However, Alice does not wish to publish this program P to everybody. This could be for various reasons. Let's say there is some proprietary information about about Alice hidden in the program P, because of which they are unwilling to distribute it. On top of that, Alice doesn't even want to either host or execute the program P locally. So rather, what Alice chooses to do is delegate the computation of this program P to some untrusted worker. You can think about this untrusted worker as some cloud service. Along with that, we have another identity, an input provider, who sends in some input X to both the worker and the users. And the worker's goal is to compute P on this input X and send it to the users. Right? This is not enough, because the user at this stage also needs to verify and be convinced that this computation was actually done correctly and honestly using the correct program P. In order to do that, the worker, along with the output of P on X, also sends some proof pi to the verifier. And the verifier will accept if and only if the proof pi is valid. So one thing I would like to point out is that it's, of course, possible for this input provider and the user to be the same identity, but we deal with a more general setup where they can be completely independent individuals and we would still be fine. So of course, we have some restrictions on the size of this proof pi. If we did not have such a restriction, then this protocol can be easily solved by using like simple non-interactive zero-knowledge proofs. However, if we have some restrictions on pi, which we'll discuss later, we do not yet know how to solve this problem where the verifier does not know what P is. So we need a little bit more help, which will be in form of a tiny amount of information about the program P as a trusted hash, which would be generated by Alice. And it would be crucial. It's crucial to assume that this hash is generated in an honest manner. So this is our setup, and our goals are the following. We want a complete non-interactive delegation. So there are only unidirectional arrows with no back and forth communication. Public verification, which means the same proof pi should work for all the verifiers. Public delegation, which means that the computation of the hash HP should be completely independent of what the input is. And there should be no pre-processing between the worker and Alice before the delegation takes place. Finally, we have some succinctness requirement on the size of the proof and the verifier runtime, where we crucially want the size of the proof and the verifier runtime to be polylogarithmic in the size of the program, and the prover runtime to be polynomial in the size of the program P. So let's, I'll just quickly go through what the current state-of-the-art works are. So if you look at interactive schemes where the verifier and workers are allowed to have interaction with each other, then we have several works from standard assumptions, starting from Killian's work in 1992. Now, in the non-interactive setting, if we are willing to have either private verification or private delegation, then again, we have a number of works from standard assumptions like LWE, FHE, etc. However, if we concentrate on our setup, which is public delegation and public verification, the only works that is known till date are starting from Silvio Micali's work in 2000 based on random oracles, and there have been several follow-ups based on non-standard knowledge assumptions. However, the only works that's known till date based on standard assumption require the verifier to know P in advance, which was started by this work from KPY19, and recently the work on SNARKs for P also achieves the same thing from, but the verifier needs to know P, which is a deterministic setup in that case. So natural question to ask is, why has constructing a protocol that caters to the fully non-interactive setup, which we've defined, been so difficult? So if you look at it carefully, the verifier does not know P, which means from a verifier's perspective, the P is like an NP witness. So when we add to it the succinctness requirement that we want in the proof size and the verifier's runtime, this problem seems intricately related to finding a solution for the SNARKs for NP problem, where the only solutions known so far are in the random oracle model or using non-standard knowledge assumptions, and finding solutions from standard assumptions have been open for over a decade. In fact, interestingly, in a very recent work of Chaudhary, Jananjan, and Fox, we've come closest to achieving that goal, where in fact, the best we could do is get SNARKs for P from LWE, where the verifier already knows what the program P is. So in our work, we give the first fully non-interactive public delegation with public verification from standard assumptions, where the verifier does not have information about what the program P is. So moving on with our contribution, we show that we can indeed bypass the requirement of having SNARKs for NP in such a setup. And what we need, and we also show that the ideas for the previous works on SNARKs for P can be used here with some modifications. Specifically, it suffices for Alice to just compute a very tiny amount of information about this program P to the verifier in form of a trusted hash HP, whose size can be as small as polylogarithmic in the size of the program. And that would suffice. So our main theorem is the following, that assuming the hardness of LWE, there exists a construction for publicly verifiable non-interactive succinct delegation for committed programs, where the CRS size, the proof size, and verified time is polylogarithmic in the size of the program P, and the proof time is polynomial in the size of the program P. I would like to stress that in our construction, in fact, the CRS size is completely independent of the program and the input. It's just polynomial in lambda, which is a security parameter. And the prover runtime is polynomial in P, which is expected because the prover at least needs to run the program completely in order to generate what the output would be. So I'll quickly introduce the formal delegation scheme setup. So we have 4 PPT algorithms. Setup, which outputs the CRS. We have a program author, which takes into input the CRS and generates a randomized program author that generates the program P, and the trusted hash, which will go out to the verifiers as well. There's a prover, which gets into input the entire program P, the input X, the CRS, and output some value Y along with the proof pi. And we have a verifier that only gets the trusted hash, the inputs, the outputs of the verifier, outputs of the prover, and either accepts or rejects the proof. So we need the following properties: the completeness, which says that for all programs generated by this program author, if the CRS is appropriately generated and the prover runs honestly, then if P of X is indeed Y, then with probability 1, the verifier must accept the proof. We have the efficiency requirements, which you already discussed, based on the verifier runtime, the size of the proof, and so on. And finally, we have the soundness requirement, which says that for any PPT adversaries, which we can split into 2 parts, A1 and A2, that upon seeing the CRS can adaptively generate the input and the proof along with the output. If the output of P on X is not equals to Y, that the prover claims to be, then the probability that the verifier accepts the proof will be at most negligible. I'll quickly go, for the sake of time, I'll just go through an informal discussion on what our techniques is, and I'll probably sweep a lot of technical details under the rug. So to begin with, we can consider the execution of a program P on X as a deterministic Turing machine that takes into input X and does some computations on it. And P will accept X if P of X is Y within some T steps, which is known in advance. So now if we look at the stepwise computation of this Turing machine and we look at what the tapes look like, what we can do is we can encode the content of the tape at every ith computation into some very succinct encoding using a hash tree. And now the work of CJJF on snarks for P shows us that if we can successfully check that H0 encodes the correct input X and HT encodes an accepting state, then we can have a snark proof that will satisfy all the guarantees that we require. So there are a lot of technical details that goes into checking, like seeing how this will work in a succinct manner, but we'll skip that for this talk. But roughly this is the idea. But however, the issue in our case is that we do not know what P is. So how do we even check what the steps of these Turing machines would look like? So we start with a different interpretation of this computation where, let's say we have a universal Turing machine that takes into input the program P, X, and the output of the program Y. And this universal Turing machine will accept the inputs if P of X is equals Y in some T prime steps, which is again known in advance. So from here, for simplicity, we can assume that this Turing machine has 4 tapes. There are 3 read-only tapes, each of which contain the program P, X, and Y. And there's one work tape where all the computation takes place. Now, again, following the blueprint of the previous slide, let's say H0 to HT prime are the succinct encodings of the intermediate steps of this universal Turing machine. And now, again, if it was possible to check that H0 correctly encodes the inputs P, X, and Y, and HT prime was the accepting state, then again, using previous works, we would be done. But it seems like we still have the same issue here because the verifier does not know what P is. So how does it even check whether the correct inputs were actually encoded? So if we just take a more careful look at what H0 contains, so H0 contains encodings of 3 things, P, X, and Y. Right, and it looks like this. So there are these 3 tapes, each of which contain P, X, and Y, and all 3 of them taken together forms H0. So of course we have a 4th tape, which is the work tape, but it's empty at when the input is just given, so we ignore it here. So now note that the verifier knows what X and Y are. So all that the verifier needs to do is use the hash function to hash down X and Y and check whether these 2 encodings match the correct hashed values. And if they do, then the verifier is happy and we're done. Now we need to look at how to deal with P here. And this is where the requirement of sending the trusted hash HP comes in from the Alice. So once this HP is generated and is fixed, now what we can do is we can simply hardcode this succinct HP to the verification circuit. And at this stage, the verifier can now test if the encodings corresponding to as a part of H0 indeed matches this HP. And if it does, then the verifier would be happy that the correct program was indeed used. And why is that the case? Let's say that some other program P prime was being used by the prover and the hash still matched. That would essentially mean that the prover succeeded in breaking the collision resistance of the hash function. So once these 3 steps, these 3 things are matched with HP, which we can do, we are now all good and we are ready to, we have everything set up where we can now use the previous work from snarks for P to use all of their steps to get the proof that we want. In fact, what we achieve here is what we call this semi-trusted snark for NP. NP because the program P is not known to the verifier, so it's an NP computation from a verifier's point of view. And semi-trusted because it's crucial that this hash is generated by a trusted party. Along with this, we also show an additional property where we give a generic transformation to convert any such delegation scheme of this type to achieve 0 knowledge. So in order to do that, instead of sending out HP in the public, what the program author does is it sends an extractable statistically binding commitment to this to HP to the verifiers. And then we can use some standard CRS appending tricks and a NIZK proof in a modular fashion to get our properties. So specifically, we do the following. So we take the CRS which we had in the previous non-zero knowledge protocol, and we append to it a commitment to 0. So since it's just a commitment to 0, the CRS still remains succinct. It was the previous one was short as well. And now, unlike the previous case where along with the why it sends the proof pi directly to the verifier. What the prover now does is, instead of sending the proof pi, sends a NISIC proof for the following statements, which says that either pi is a valid proof for the verification circuit, or the CRS contains a commitment to 1. So now if you look at this, in the real world, everything is still the same because we added a commitment to 0 in the CRS. So for the proof to work, the prover actually has to send a NISIC proof corresponding to the first statement, which where all the properties goes through. However, in the simulated world, what the simulator can do now is just when the simulator generates a CRS, it can switch the CRS to having a commitment to 1 and send a NISIC proof for the second part of the statement and completely ignore the proof pi. So the proof that now goes out does not contain any information about pi, so it's completely zero knowledge. And we are able to make these switches because of the necessary hiding properties of the commitment scheme and witness indistinguishability of a zero knowledge or a NIVI proof. So with this, we come to the end of the talk. Thank you, and I'll take questions.
Any questions? All right, so I think this delegation, succinct delegation reminds me a bit of functional commitments. Can you comment on what the similarities or differences might be?
I'm not quite sure how the two primitives would be related, particularly because here in a delegation scheme, what we are looking for is a succinct delegation scheme. So the size of the proof, the verified time, and so on is important. And I'm not very aware how that relates to the functional commitment paradigm.
Okay, thanks. We don't have any more, no more questions. All right, so let's thank the speaker again. Next, we have laconic functional evaluation for Turing machines by Nico Dödling, Philip Gayland, and Giulio Malavolta. And Philip Gayland will be giving the talk.
Can you hear me? Okay, thank you for the introduction, and thank you very much for staying around until the last talk. In this presentation, I'll be talking about some joint work with Nico Dödling from CISPA, Giulio Malavolta from MPISP, and my name is Philip Gayland, and our paper is entitled Laconic Function Evaluation for Turing Machines. Let me start with a brief outline for the talk. So I'll first present laconic function evaluation and its applications, if you may not be familiar with this primitive. Then I'll highlight some prior work and address the problem statement. And finally, I'll present our results and some new applications. So let me dive right in. What is laconic function evaluation? So laconic function evaluation was introduced by Quax, Wee, and Wix at Fox 2018. It's a cryptographic primitive. We've got Alice on the left, Bob on the right. Now, Alice has some large function f that she can compress into some digest d. Given this digest, Bob can encrypt some input x under this digest and send the resulting ciphertext back to Alice. And given the ciphertext, Alice can decrypt it and learn f of x. We also want Alice's digest will, of course, depend on the function f. So if there's a different function, she'll get a different digest. The laconic property says that we want the digest to be short because Bob has to read it. And we want Bob's ciphertext to hide x from Alice, but of course, Alice will learn f of x in the clear. And additionally, here we want the laconic property to mean that the ciphertext that Bob computes should be efficient to compute. So to make this a little less abstract, imagine Alice is Google, and Bob is using some resource-constrained device such as his mobile phone, and Alice wishes to run some complicated algorithms on Bob's input. So for correctness, we want that decrypting the ciphertext under the function f to be the same as just evaluating f of x. And for efficiency, we want Bob's work to be small. So marked here in green, you will see that the digest, the size of the ciphertext, they're all small, and also the time for running the encryption procedure should be small. But as there's no such thing as a free lunch, Alice will have to do some extra work. And that's marked in red, so the compression function and also the decryption procedure will be costly. So for security, again, we want the ciphertext to hide x, and Alice will, and it should only reveal f of x to Alice, no more. So let me present some applications of this primitive. So naturally, it seems very well suited to that of succinct two-party computation. The setting that we consider is we have some function f. Alice has some input, Bob has some input, xa and xb respectively. And sort of the best we can hope for is that Alice sends one message to Bob and Bob sends one message back to Alice. That's sort of the minimum we can hope for and sort of the best we can try to achieve. And at the end of it, Alice will learn f of xa and xb. Now, here the security is that Alice will learn f of xa, xb, and Bob should not learn anything. And we have some efficiency constraints that say communications should be small. And then the computation for one party, so either Alice or Bob, should be a lot less than just computing f of xa, xb in the clear. So there are two settings that we can consider. The one is that of a so-called Alice optimized protocol. So we see here, Alice is resource constrained and Bob has to do all the heavy lifting. So this can be realized using fully homomorphic encryption as follows. So Alice would encrypt her input xa using some homomorphic encryption scheme, send the ciphertext to Bob. Bob would evaluate f of b on this ciphertext and send the resulting ciphertext C prime back to Alice, who decrypts it to learn f of xa, xb. So here, marked in red, you see that, of course, this FHE evaluation is going to be costly, but Alice's work, the encryption and decryption, is relatively speaking cheap, and that's why it's marked in green here, but the communication is still small. So a natural question is, can we come up with a sort of dual notion, which is that of an Bob optimized protocol? And the answer is yes, we can. We can do that using a function hiding version of laconic function evaluation. So how does it work? So just to recap what we're considering here. So here, Bob is resource constrained and Alice is doing all the heavy lifting, right? So that's why Alice is big here, Bob's small. So it works as follows. Alice compresses the function fa into this digest, sends it to Bob, who then encrypts his input xb, and at the end of it, Alice learns f of xa, xb. Okay, so here the expensive stuff is, again, the compression and the decryption. So that's why it's the Bob optimized version. Okay, let me say a little bit more about some applications. So apart from the succinct two-party computation that we get, the work of Quarksui and Wicks also showed that you could get multi-party computation with low online computation. And some work by Cohen, Shalat, and Wicks showed that you could get multi-party computation with adaptive security and very low communication complexity. A recent work from crypto by Katsumata et al. Shows that you can use laconic function evaluation in a black box manner to get NISICs with interesting prover complexity. But the techniques that we use for constructing laconic cryptography actually have led to many, many other applications, which I'll list here. I won't go into much detail on these, but just to say that these techniques have been used elsewhere as well. Okay, so now let me just say a few words about some prior works that sort of motivate our work. And of course, I want to start by addressing the first work on LFE, which uses techniques from functional encryption and attribute-based encryption to construct this primitive. And essentially, they just rely on the LWE assumption. Then a follow-up work by Pan et al. Showed how to get multi-input laconic function evaluation, but they require stronger assumptions. In particular, they require indistinguishability obfuscation. And a more recent work of Rosie from 22 showed how you could get adaptive security for like a limited class of circuits. In fact, they show adaptive security for NC1. So that's all polynomial size circuits with logarithmic depth. These are the three constructions of LFE that have been considered so far in the literature. But unfortunately, one problem with all the prior works is that the ciphertext that Bob sends, and also the runtime of this encryption procedure, they actually grow polynomially in the depth of the circuit, right? So there's no dependence on the size of the circuit, but there's a dependence on the depth of the circuit. And I want you to think of this as, maybe you've heard of leveled fully homomorphic encryption as opposed to sort of pure fully homomorphic encryption. And that's sort of the difference here. And the question is, is this inherent, or can we actually get rid of that? So more specifically, is it possible to construct laconic function evaluation where the size of the ciphertext and the runtime of the encryption procedure are independent of the circuit depth? So that's where our contribution comes in. So what we answer this question in the affirmative, and we show the following theorem very informally here. So assuming indistinguishability obfuscation and a primitive that I will talk a little bit about in the following slide, updatable laconic oblivious transfer, we get a laconic function evaluation scheme for Turing machines with the following parameters. So just to remind you of what the parameters are. So the function digest, the size of the function digest that Alice has to send is just a polynomial and the security parameter. The time for Bob to run the encryption procedure depends on his input, of course, because he has to read his input. And then there's just a multiplicative factor that's a polynomial and the security parameter. And similarly, the size of the ciphertext also only depends on the input and then has a multiplicative factor that's a polynomial and the security parameter. So how do we do this? Let me say a few words about the construction. So the construction is as follows. So I mentioned that we will need indistinguishability obfuscation. So a 5-second introduction to I/O. So assuming you have two circuits, C0 and C1, that are functionally equivalent, meaning that when they're evaluated, when they're run on the same inputs, you get the same output. Well, two functionally equivalent circuits, their obfuscations should be computationally indistinguishable. The next building block that we will use, that I showed you in the previous slide, was that of this oblivious transfer protocol. It has some interesting properties. It's laconic and has this updatable feature. So how does it work? Alice has some large database D that she can compress into some digest and send to Bob. Now, what will Bob do? Bob will specify one location in her database and send her two messages, M0 and M1. And at the end of this protocol, Alice will only learn the message that corresponds to the value that is stored in the database that Bob specified, right? So it's an OT protocol that is laconic because this database could be very large and we can compress it, and it's updatable because that's a little technicality, but basically you can update the digest without having to recompute this whole hash. We will also use some other tools, but I won't go into much detail here. So basically, we also need garbled circuits. I mean, they are kind of implied by this, but yeah, I don't list it here. And we'll also need puncturable pseudo-random functions, but that's sort of a technicality of the proof. So these are the sort of main building blocks. So let me try and present the construction at a very high level. So we have three procedures that we're interested in. We have the compression function, we have the encryption procedure, and the decryption procedure. So the compression works as follows. We basically just call the laconic OT hash, and that digest is just sent straight to Bob. It gets a little bit more tricky with the encryption procedure, but it can sort of be distilled to two main parts. So the one is that Bob will have to encrypt his input. So he does that using some symmetric encryption scheme. And then he does this thing, which I call the step circuit. So what I want you to imagine now is that the Turing machine has some transition function. And this transition function is encoded as a circuit. And this circuit, I call the step circuit here, performs one step of the computation. Now, of course, the step circuit, when Alice runs it, will leak the intermediate computations to Alice. So we want to hide those somehow. So how do you do that? We actually garble this circuit. Now that would mean that Bob would have to send many circuits over to Alice, and we would no longer get this laconic property. So what we can do is that Bob obfuscates one single circuit. So he obfuscates this step circuit. And what does the step circuit do? I said it performs one step of the computation. And then additionally, it will use this laconic OT protocol to write the intermediate outputs to the database. So just bear with me for a second what happens. So Bob will send two things. He will send the encryption of his input, and he will send this obfuscated garbled step circuit. Now Alice, she will run this obfuscated step circuit for each step of the computation. And she will call this oblivious transfer receive function in order to get the inputs that she needs for the next step. So she's running, there's a garbled circuit there, so she needs labels, and those she will get using this OT receive procedure. And then the final step will be the output f of x. So when she's run every single step, then what she is left with is f of x. Okay? So that was a very high level overview. How do we prove this? So we use a technique very similar to that of Garg and Srinivasan from TCC 2018. And yeah, we use it's a pebbling strategy. It's very nice. Yeah, that's all I will say about it. Maybe I say a few more words. So basically, the pebbling strategy works as follows. You have, you can imagine you have a number line. You have white pebbles, gray pebbles, and black pebbles. The white pebbles can be thought of as the construction as is, and the black pebbles can be thought of as everything being simulated. And then you have these gray pebbles in between, which represent something intermediate. And then the question is, how can you change the colors of these pebbles? You have to set some rules when you can change from white to gray and from gray to black. And then you can basically show that you don't have to do enough, you don't have to do very many swaps in order to get to the black configuration, which would then show that it's everything is simulated. Okay, so let me just say, finish with some applications that we get. So using the work from Katsumata et al. From crypto, we actually get NISICs with optimal prover complexity. We also get witness encryption where the size of the ciphertext only depends on the size of the witness and the security parameter. This is quite cool. So there's no dependence on the size of the NP relation or the size of the instance. And as a result, we get an attribute-based encryption scheme for Turing machines from falsifiable assumptions, which was not previously known. So let me conclude my talk with the following slide. So what did we show? We showed an asymptotically optimal laconic function evaluation scheme for Turing machines. So where the size of the ciphertext and the runtime of the encryption procedure do not depend at all on the size of the function. We get some nice new applications, namely that of NISICs with optimal prover complexity, witness encryption, and attribute-based encryption for Turing machines from falsifiable assumptions. So the paper's online on this link, 2023-502. That concludes my talk. Thank you very much.
Any questions?
Thanks for the talk. So in the definition of laconic function evaluation, so the function f, so when Bob receives this function digest from Alice, is there any property about how some like maybe Bob should not know what function f that Alice wants to compute on? Or...
That's right. Yeah, great question. So there's a notion of function hiding, right? So for this succinct, I think I showed it here. Yeah, so for this application for the succinct two-party computation, we actually use a function hiding version of LFE, right? So if it's function hiding, then this will be this part, the compression algorithm will be deterministic. Yeah. So yeah, to answer your question in short, yes, there is a version where you can hide the function from Bob. Yes.
Thanks.
Yeah, and just to say that there is like a generic compiler that takes an LFE scheme and turns it into a function hiding one. So yeah.
Any other questions? All right, let's thank the speaker again. Next, we have a map of witness maps, new definitions and connections by Sarvadit Chakraborty. Manoj Prabhakaran, and Daniel Wicks. And the speaker will be Suradip. Sorry.
Hello, am I audible? Good. Okay, so this talk will be about a map of witness maps, new definitions and connections. And this is a joint work with Manoj and Daniel. Okay, so let me start the talk with the following observation. Suppose we have a room full of mathematicians, which probably is true. And then we have a theorem statement. Think of your favorite theorem statement that you want to prove. I give these theorem statements to all the mathematicians. They're separated, they don't talk to each other. And then I ask them to write down the proof of this theorem. And they give me back the proofs. And then I ask, what is the probability that each of them write down the same exact proof for the theorem X? And the answer is highly unlikely that they will write down the exact same proof. I mean, the essence of the proof might be the same, but the strategies will differ. So interpreting this in the context of computer science, for NP languages, you'd want to ask the question, for an NP language, we'll have like multiple witnesses. Like, for example, a graph 3 coloring will have like possibly exponentially many colorings, right? So the question that I want to ask is that, can we come up with a proof system, preferably for NP languages, where the proofs are guaranteed to be unique? So this corresponds to the complexity class undeterministic, unambiguous non-deterministic polynomial time complexity class, UP in short. And so the question is that, is NP equals to UP? So does all NP languages have a unique proof? And the answer is unlikely. And in fact, there are results which Oracle separate these two classes. But in the context of proof systems, so in our work from PKC 2020, we showed that one can come up with a computationally sound proof where for a particular NP statement, one can come up with a unique proof. So think of the left-hand side which is the witness space. And there is a mapping algorithm, which is deterministic, which takes as input a CRS that is generated at setup, takes the instance and any arbitrary witness, and maps to the same proof W star. So the map is deterministic. So I call this the witness set, and this is the canonical representative witness. So since this is the canonical proof for this statement X. So more formally, the setup generates the CIS. So the map is deterministic, produces the proof. And there is also a verifier, which is efficient and takes the statement and the proof and outputs 1 or 0. The properties that we want is completeness. If the statement is true, the canonical witness should check. Soundness says that if the statement is false, then you cannot come up with a convincing proof. And now instead of zero knowledge, the property that I want is uniqueness, which means that for each statement X, I have a unique proof, which means that the proof is independent of the witness. So it does not matter which witness you use, you basically collide to the same proof. So if you think this is basically NIMI, because all the witnesses map to the same proof, this is a NIMI with a deterministic prover and verifier, okay, and which has computational soundness. So another relaxation of unique witness map is something called compact witness maps. So here, instead of saying that I map everything to one proof, so here I map it to a much smaller set of proof. So I'll call this set S. And as before, the algorithms are the same, and I want the same completeness and soundness guarantee. But instead of uniqueness, I want alpha lossiness, which says that the size of this set S is bounded by 2 to the alpha, where alpha is some compactness parameter. So note that UWMs were a special case where alpha is 0. So you map to the same proof. Okay. And I also define another variant, which will be useful. This is nothing but the designated verifier variant of UWMs, where there is a setup which generates a CRS and a secret verifier key. And while verifying the proof, you need the secret key. else all the components are the same as a UWM. And of course, you can generalize it to a compact witness map as well. And for soundness, it required that if the statement is false, then the proof should not verify. If the adversary has no information about the secret key other than seeing the CRS. But you can define a stronger property, which we call reusable soundness. So since the secret key is used for checking, the adversary can also submit proofs and statements and check whether they're true or false. So the here you also want the property that if the statement is false, the proof should not verify. But here, even if the adversary gets Oracle access to the verifier. Okay. So what do we know about prior results on witness maps? So from our PKC paper from 2020, we showed that UWMs have applications in the area of leakage and tamper resilience. We showed that this primitive can be constructed from IO and one-way function. And we show that this primitive is quite strong because it implies witness encryption. So this is like the new kid in the block of Officetopia. Okay. And in fact, we show that even if you relax unique witness map to alpha CWMs, where the set of proofs is polynomial, it still implies witness encryption. Okay, so in this work, we basically take a thorough study of witness maps and connect them to other crypto primitives. And we believe it contributes to the study of functional compression in the same spirit as in obfuscation, because we know XIO versus IO, for example. So what we achieve in this paper, so the dotted arrows are trivial implications. So UWM implies an extremely CWM, which implies a mildly CWM. When I say mildly, I mean the alpha is said to be P of lambda, where lambda is a security parameter and P is some fixed polynomial, independent of the size of your statement and witness. Okay, so from the prior work, we know that IO implies UWM. And in this, and UWMs imply the designated verifier variant because it's more general, because it's publicly verifiable UWMs. So in this work, we show that, well, the weaker variant of designated verifier UWM implies witness PRF. So I'll shortly define what's a witness PRF. And in fact, these two notions are equivalent. And we also show that UWMs imply NISIX, where the prover can be deterministic. And earlier from the work of Sahai Waters, we know that IO and one-way function implies deterministic prover NISIX. So this places designated verified UWM somewhere between witness PRF and IO. Okay. And we show that when the set of all proofs is some polynomial, that is alpha is some big O of log lambda, this implies pseudo unique witness maps. So what is pseudo UWM? So these are like pseudo deterministic algorithms where so this algorithm has random coins, but still behaves like a deterministic algorithm. So regardless of the random coin that you put in, that you feed into this algorithm, it will output the same result with high probability, where high means 1 minus 1 over poly lambda, where I can arbitrarily set the polynomial P. And we show that this primitive is as good as uniqueness in the sense that this implies witness encryption. And earlier from our previous work, we showed that UWMs imply witness encryption, but now you could relax this a little bit. And now we show that if you increase alpha to be a fixed polynomial, this implies NISIX, which is surprising. And if you think about it, Schnarks imply this mildly CWM because Schnarks are proof systems, so the proof is short. And here I'm asking that the proofs might not be short, they can be long, but the number of proofs are 2 to the poly. So if the proof size is some poly, so the number of proofs, possible proofs, is also 2 to the poly, right? So Schnarks imply mild CWMs, and mild CWMs we show implies NISIX. So mild CWMs are somewhere in the picture between Schnarks and NISIX. Good. And finally, we show a complexity theoretic result where we show that if you have like statistically or perfectly sound UWMs, that implies NP equals to UP, which we don't believe to be true. That basically says that you cannot have UWMs that are statistically secure. So you need computational soundness. Yeah. So for the purpose of this talk, I'll just talk about the first block, that is the implications between witness PRF, and I leave the rest to look up in our paper. Okay, so I will show that designated verified UWMs and witness PRFs are equivalent. So let's first show the first trivial direction. Okay, so before showing that, let's define what's a witness PRF. So witness PRF is like a PRF, but that the PRF can be evaluated in two ways. First, you have a secret key Fk, and it takes as input X, outputs Y. But there is another mode of evaluating the PRF, which takes a public key, that's the evaluation key, takes an X, a statement, and a witness, think of it as an NP statement, and outputs Y prime. And you require that if X is in the language, these two evaluations are consistent with each other. Whereas if the security says informally that if X is not in the language, the value is still pseudo-random. So the game is like the adversary gives an X star that is not in the language. It generates the keys. It sends a public key to the adversary. The adversary can ask different statements Xi and receive evaluations, the PRF evaluations. And it can continue arbitrarily poly times. And finally, it enters into a challenge phase where the challenger either computes the PRF using Fk. Note that X is not in the language, so you cannot compute in the public mode. So you have to compute in the private mode. So it computes either the true value Y0, or it randomly samples the value and returns Y sub B to the adversary, and it has to guess the bit B. Okay. Now we call this static instance interactive security. Why interactive? Because the adversary interacts with the challenger, and it's static instance because X star is given upfront. One can think of an adaptive variant, but for our purpose, this is enough. And if you remove the interaction phase, we call it non-interactive security, or NI. Okay. Okay, so let's first show the trivial direction that witness PRFs imply DVUWM. So the construction is very simple. So the setup of the UWM is just running the key generation, and you set the CRS to be the public key and your verification key to be the secret key. The mapping algorithm is just evaluates the PRF and sets the proof to be the Y, the output of the PRF, and checking algorithm is basically it takes a statement X, the secret key is Fk, so it outputs Y prime and checks whether W star is equals to Y prime. Okay, and so this is complete. This is unique because note that the algorithm WPRF.F does not take the witness as input, so it deterministically maps X to W star. And this proof I'll skip for now. It's just follows from the interactive security of witness PRF. Good. So let's go to the other direction. So where we show that UWMs imply witness PRF. So here it's a bit more complicated, but still simple. So the key generation algorithm runs the setup of our map, and additionally it samples, it outputs Y, which is computed as G of Z, where G is a length doubling pseudo-random generator. And then I set up the public key to be CRS and Y, and the secret key is basically the pre-image of the PRG. And now the private evaluation algorithm works as follows. Consider the statement that X is in L or Y is pseudo-random. Okay? So now I can compute the map using the pre-image of my PRG as a witness. And now I can take this W star and compute the Goldreich-Levin hardcore bit, and this is my pseudo-random bit. Okay, now how does the evaluation work? The evaluation, recall that it knows the witness. So it can take the witness to compute the same output for the statement X hat, because it knows the W for the first part of the branch. Okay? And it can recover the Goldreich-Levin bit, and yeah. And basically the correctness of WPRF says that these two values are equal. Okay? And so the proof intuition is that if an adversary can distinguish between bit 0 and 1, using Goldreich-Levin decoding, I can compute a value X star, which passes the verification check. Now I switch the PRF value to be PRG value to be pseudo-random. At this point, the statement is false because X is not in the language, and the value y is random. But then still W star is a valid proof. So which is a contradiction to UWMs. And finally, for the last part, we show that for witness PRF, non-interactive security and interactive security are equivalent. And this was not known to be true. So in the original paper of Zandri, he showed some applications that required the stronger interactive security, but here we show that it's possible to generically upgrade it. So the idea is very similar. You run the setup of the non-interactive witness PRF, and then you commit to some junk. So when I say junk, it means some like a string 0, which is not in the statement space, using randomness R. Okay, and this is statistically binding. And you set your public key to be the public key of the non-interactive PRF and the commitment, and the secret key is the secret key of the non-interactive PRF and the randomness of the commitment. And again, I consider an OR kind of language where I consider X is in the language, or you commit to some string which is not X. Okay, and then basically the evaluation works by committing to 0 because it knows R, and then it outputs the private evaluation on the statement exec, and the public evaluation works because it knows the witness W. And the proof basically is that it switches the commit. So when the adversary gives X star, it switches commitment to 0 from commitment to X star. And then the evaluation queries are answered because you know the randomness. Okay? And then basically you switch the way that the witness PRF is computed. So you go from the private mode to the public mode. And then we show that in the advantage of this adversary in this final game is negligible. So I conclude with some open problems. So it will be interesting to explore witness map and other cryptographic primitives in the way that how they connect with each other. For example, does witness map imply Schnarks? So I've shown that in the diagram that Schnarks imply witness map, but we don't know about the other direction. Well, even if not, is it possible to black box separate witness maps from falsifiable assumptions? Also, this is interesting. Does witness map imply one-way function under some complexity theoretic assumption? Like, for example, NP not equals to RP. So for IO, we know that IO plus this complexity theoretic assumption implies one-way function, but we don't know about that for witness map. And finally, can we come up with more applications of witness map? And that will be my talk. You can look up the paper for further details. Thanks. And I'm up for questions.
Any questions?
Oh, hi, thanks for the presentation. Yeah, I was wondering, you said that we can construct this UWM from IO, right? So on the other direction, like if for every program we have a unique representation, then it's naturally an IO, right? So can you comment on why this UWM cannot imply IO, or do you see why it is difficult to construct IO from UWM?
So we have not thought about this, but in spirit, these two seem to be very different kind of primitives. This is like a proof system, and like yeah, actually I'm not sure. Like, how do you even compare the two primitives, like IO and witness maps? So we know that like the designated verifier variant is equivalent to witness PRF, and we have shown certain applications that follow from IO, but for example does not follow from witness PRFs. But I don't know if we can generically replace IO with UWMs, and I think that's a very interesting question. Yeah.
Any other questions? Could you say a little more about the pseudo UWM? Like, what situations might you need actually like the full UWM instead of the pseudo notion?
Yeah. So so the pseudo UWMs are basically UWMs where if you take two witnesses, it will map to the same proof with very high probability, and you can use the pseudo UWMs instead of UWMs in any application where you can error correct. For example, when you try to construct witness encryption, it will result in a decryption error of 1/poly. But then you can repeat this exponentially many times with independent randomness, and then you can take the majority and still get the same applications that unique proofs will give you. So I think pseudo UWMs, you can use it as a drop-in replacement of UWMs in any applications where you can error correct.
Thank you. All right, let's thank the speaker again, unless there's some questions. Finally, we have last talk of this session is structure preserving compilers from new notions of obfuscation by Matteo Campanelli, Danilo Francati, and Claudio Orlandi. And Danilo will give the talk.
Okay, thank you for the introduction. So this is a joint work with Matteo Campanelli and Claudio Orlandi, and what we're gonna see are alternative notions of obfuscations. We're gonna see the applications. We're gonna study their feasibility and the relation with the other notion of obfuscation we have. So let me start with the definition of an obfuscator. We care about circuits, and an obfuscator is a program that takes an input a circuit and outputs an obfuscation. We want some basic properties. So the obfuscation preserves the functionality of the original circuit. And also we want a polynomial slowdown that says that the obfuscation is not so big compared to the original circuit and must be polynomial in the size of the original circuit. So now let's talk about security. We can define security in different ways. We need to play with three different aspects. And according to their combination, we obtain different level of security. So the first one is how you define the leakage. So what kind of information you leak. You can use a simulation-based definition, or you can use an indistinguishability-based definition. The second aspect is about distribution. So maybe the security guarantees only holds if you sample a circuit from a particular distribution, or maybe not. So we're going to have these two cases. And when we care about distribution, we're going to assume that we have a sampler that gives you an output either one or two circuits, depending on the definition of some auxiliary information. And lastly, also about the functionality, because the security may hold only if the circuit computes a particular type of function. So maybe you don't have any restriction and you can obfuscate any circuit, but in some cases, especially with indistinguishability-based definition, you want to, I mean, you have the security holds only if you compare similar circuits, in some sense. So we're gonna see now the existing notion, and I'm gonna assume that there are samplers everywhere just for simplicity. So these are the most famous notions. So we have virtual black box, VBB, different input obfuscation, DIO, and indistinguishability obfuscation, IO. Let me start with VBB. So in VBB, we have that the obfuscation technically can be simulated by a simulator that has only Oracle access to the circuit. So this means that the obfuscation doesn't leak anything except from the input-output behavior. And okay, in the definition, I mean, the auxiliary information is given input both to the adversary and the simulator. So for VBB, this is the situation. We have a simulation-based security, samplers, and I haven't said much about the functionality. So technically speaking, you can obfuscate any circuit. Why we like VBB? Because VBB is magic. So you take a circuit, you obfuscate it, and you have like an oracle. So the only thing you can do is to give an input and see the output. And one of the most famous application of VBB, at least the initial one, was to do structure preserving compilers. What does it mean? So suppose you have a symmetric key encryption scheme and you want to convert it into a public key one. What you can do, you simply define this circuit here in which you are code a key, and and the circuit is going to compute the encryption algorithm. You obfuscate it, and now you set the public key equal to the obfuscation, and you have a public key encryption scheme. This is called structure preserving simply because what we are going to obfuscate is simply the encryption algorithm of the symmetric key encryption. Or if you need to change a little bit the definition of the circuit, it's important that the output has the same format of the original circuit. So for example, of the original algorithm. So here, for example, the ciphertext has the same format after the compilation. So unfortunately, there are impossibility results for VBB. So we know that there are circuits that you cannot obfuscate unconditionally. And also the existence of these circuits implies that there are applications that you cannot do no matter what, and no matter what kind of definition of obfuscation you use. And one of them is precisely this compilation. So you cannot go from symmetric key encryption to public key encryption, no matter what kind of obfuscation you use. But I want to stress that the impossibility result applies to this kind of construction. So you cannot do the conversion if you simply obfuscate the encryption algorithm how it is defined here. So maybe theoretically speaking, there could be another way, but we don't know. Other definitions. So we have I/O. Suppose now we have a sampler that gives you in output 2 circuits. If the circuits implement the same functionality, so they have the same input-output behavior, then you can securely obfuscate them. But now the definition is indistinguishability based, so you cannot obfuscate between the first and the second one. And what about the I/O? Now the I/O, it's we have still a sampler that gives you an output 2 circuits, and the security says that of the sampler says that output 2 circuits that have differing inputs. So you cannot find an input of which they differ. And this must hold also even if the adversary has access to the code of the circuit. So you can look at the information inside. Now, if you have them, then you can securely obfuscate them, usually according to the same distinguishability based notion. So for I/O and the I/O, this is the situation because we have an indistinguishability based definition, samplers, and also we care about the functionality because we are comparing similar circuits in some way. Now, what are the limitations of these primitives? I mean, they're very powerful, of course, but they are not able to implement the structure preserving compilers of VVB, for example. And the intuition is because when you want to do this compiler, you want to hardcode into the circuit a secret, but when you do that, you are not going to be able to use I/O or the I/O because you're not going to satisfy the functionality of the sampler. So the question that motivates this work is the following. So if you can identify weaker notion of obfuscation that compared to VVB, but are still powerful enough to do this kind of compilation. The speed, this was our initial question. We believe that studying this notion is important, even because the research on VVB is not dead, and there are papers showing that you can obfuscate particular class of circuits, and since our definitions are going to be weaker, maybe we can identify new classes. So the notion that we introduce are the following. So we have Oracle differing input obfuscation, Oracle DIO, and Oracle indistinguishability obfuscation, Oracle IO. So let me start with Oracle DIO. In Oracle DIO, we have still a sampler that gives you an output 2 circuits. There are differing input circuits again, but they're differing input only when they are treated as oracles. So the adversary tries to find a differing input, but by having all Oracle access to the circuit. Now, if you have this kind of circuits, you can securely obfuscate them using the usual indistinguishability based notion. Oracle IO instead, we have that the sampler gives you an output these circuits that are indistinguishable. That an adversary cannot distinguish if you have Oracle access to the first one or the second one. Now, if you have them, you can usually, you can obfuscate them securely according to the definition. And again, circuits are secret, so you cannot look inside the circuit. So what are the definition between these notions? So they're all indistinguishability based, at least these ones. And so the only reason why one is bigger than the other is the definition of the sampler. Indeed, if you take the samplers of IO, we know that the IO can obfuscate these samplers because if you have circuits that have the same functionality, you don't have a different input to find. With Oracle DIO, now we can obfuscate whatever DIO can obfuscate, simply because if you cannot find a different input when you have access to the code, you cannot find a different input when you have Oracle access to the circuit. And Oracle IO can obfuscate whatever Oracle DIO can obfuscate, because if you cannot find a different input, then the circuits are identical and you cannot distinguish. So this is the relation. And what about now our definitions and VVB? Well, at the very high level, we have that VVB, it's stronger than our definitions because VVB is simulation based. And technically speaking, the definition tells you that you don't leak any information because you can simulate it. But our definition can theoretically leak something, but the important thing is that what you leak does not allow you to distinguish. Okay, so our objective is to do structural preserving compilers. So let's see what, for example, Oracle.io can do. So we cannot do any compiler like VBB because Oracle.io is weaker, but we can do some of them. So for example, we can go from designated verifier to public verifiable non-interactive argument systems. We can go from MAC to signatures, and we can go from symmetric key encryption to public key encryption. But now under the constraint that the symmetric key encryption is IV-based, and IV-based essentially means that the randomness is giving output as part of the ciphertext when you encrypt. So like in any initialization-based, any symmetric key encryption that use an initialization bet. So to give you a high-level overview of how to use this assumption, let's see the first one. So we want to go from designated verifier to public verifiable. So designated verifier, we have a setup that outputs the CRS and the verification key. And the proof algorithm takes the CRS, the statement, and the witness and produce a proof. And the verification algorithm takes the verification key, the statement, the proof, and outputs a decision bit. We care about selective soundness. So for every X that is not in the language, it's going to be hard for an adversary to produce a proof that verify. And we need to note here that the verification key is kept secret, and the adversary has only Oracle access to the verification algorithm. This public verifiable is essentially the same, but now we don't have a verification key, and we verify using the CRS. So how we can convert one into the other? Well, this is the compiler. You simply need to do the following. So on setup, you generate the CRS and the verification key of the designated verifier, and then you obfuscate this circuit here. That is simply the obfuscation of the verification algorithm with coded the verification key. And now you output a CRS that takes that is composed by the CRS of the designated verifier and the obfuscation. To prove, you simply run the proving algorithm of the designated verifier, and to verify, you run the obfuscation. Now, this is secure because let's assume that we have this other circuit here in which you code a statement, and you always reject without verifying when you receive a proof that that statement, X star. Now, if you define this sampler here that outputs the first and the second circuit and some auxiliary information that is not going to be important for the talk. So what we can prove is that for every X not in the language, this is an Oracle.io sampler, because the circuits differ only when you produce a proof that verifying the first circuit, but it doesn't in the second one for X star. But this is essentially a forgery for the designated verifier. And we can do a reduction, but we can do a reduction simply because we have oracles in this case. So we can simulate the behavior of the circuits using the oracle that we have in the designated verifier experiment, the verification algorithm. So now that we know that, we can obfuscate, we can replace the obfuscation with the first one with the second one. So we replace this with the obfuscation of the second one. And now the advantage in this game is going to be 0 because we always reject for X star. In the paper, we have some other results that we're going to go over very briefly. Regarding Oracle.io, we can show that we can go from symmetric key encryption to public key encryption. But now the original symmetric key one needs to be key indistinguishable. So you cannot distinguish under which key you encrypt a ciphertext. And we also we extend the impossibility results of VBB to our case. So we modify the impossibility, and we show that even these definitions have unconditional impossibility results. So there are circuits, samplers that you cannot obfuscate no matter what. And also, we show a new impossibility of the application, in particular this one. So we cannot go from key indistinguishable symmetric key encryption into public key encryption. And this is a kind of strengthening of the impossibility results that is in the paper of VBB, because now we know that also if you assume additional properties of the symmetric key encryption, we cannot do the compilation. And let me conclude the talk with the following. So I told you that also Oracle.io can go from symmetric key encryption into public key encryption. But what about the impossibility of the application? So it doesn't apply here, simply because Oracle.io is weaker. And this weakness requires to obfuscate a much more, fairly more complex circuit. Indeed, we need to use puncturable PRF here. And the fact that the compilation that we need to do is different doesn't allow us to extend the result. So theoretically speaking, maybe that this kind of compilation is feasible. There could be an obfuscator that can do it. So that's all, and thank you.
Any questions?
Thank you. Thanks for a nice talk. And excuse my ignorance, but can you summarize these new notions at the end of the day? Are they achievable or not, or conditionally, or?
So what we show is that they are not achievable generically. So there is a class that you cannot obfuscate unconditionally. So we have the same kind of situation with BBB. Now the question is, that is an open problem for the moment, if you can identify new class. So in BBB, we can identify some classes that we can obfuscate in a BBB fashion. Since these are weaker, maybe we can identify new classes. This is an open problem.
That makes sense. Thank you.
Any other questions? All right, let's thank all the speakers again.